The question of what would really happen if a human being could travel at the speed of light is one of the most fascinating thought experiments in all of physics. It captures both the imagination and the hard limits of science, straddling the line between what we can dream of and what the laws of the universe appear to forbid. For centuries, humanity has looked up at the stars and wondered whether we might someday leap across the cosmos in an instant, traversing the unfathomable distances that currently take light thousands or even millions of years to cross. The temptation of light speed lies in its promise, the ability to make the universe suddenly accessible, to turn impossibly long journeys into instantaneous ones. But when we peel back the layers of physics, what emerges is not a simple yes or no answer, but a deeply intricate picture that pushes the limits of our understanding. The first thing to recognize is that the speed of light is not just fast, it is the ultimate speed limit of reality as we know it. Light doesn't just outrun rockets, planets, and even the fastest human-built spacecraft. It moves at a velocity so immense, about 300,000 kilometers per second, that it is woven into the very structure of space and time. The speed of light is not an arbitrary number. It defines the relationship between space and time itself. Every law of physics that governs motion, energy, and causality is anchored to this constant. To challenge it is not simply to go faster, but to disrupt the very framework of reality. When we ask, what would happen if you traveled at the speed of light? We are actually asking a deeper set of questions. What is time? What is space? Can reality bend in ways our everyday intuition cannot grasp? The hook here lies in the paradox. While we imagine light speed travel as a pathway to limitless exploration, the truth physics suggests is that it may be a pathway to timelessness, stillness, and even annihilation. Rather than freedom, light speed could represent a kind of prison, one where time stops, distances vanish, and the universe ceases to exist in any recognizable form. To set the stage for this exploration, it's crucial to understand why this question is so compelling. Every science fiction story that touches on faster-than-light travel is tapping into a fundamental yearning in human beings, the desire to break free from the limitations of our small planet and our finite lifespans. Our technology today allows us to travel around Earth in hours, reach the Moon in days, and send probes to the edge of the solar system in decades. But the stars beyond remain so distant that even our fastest spacecraft would take tens of thousands of years to reach the nearest one. At our current pace, interstellar travel is not just slow, it is effectively impossible within a human lifetime. Light speed then becomes the magic key. If only we could match light itself, the entire universe would open to us. Galaxies that are now hopelessly out of reach could become destinations. But here lies the intrigue. Physics suggests that light speed is a boundary that cannot be crossed, not merely because our engines aren't strong enough, but because the very laws of the cosmos prevent it. Asking, what would happen if you traveled at the speed of light, is like asking, what happens if you divide by zero? The equations don't just give strange answers, they break down completely. It's a question that takes us into the deepest mysteries of relativity, quantum physics, and the nature of reality itself. Still, by exploring it carefully, by examining what happens as we approach light speed, we can piece together a picture of what light speed travel would mean, even if it remains unattainable. The effects that occur near light speed are not science fiction. They are real, measurable consequences of Einstein's theory of relativity, confirmed again and again by experiment. High-speed particles in accelerators, for example, already experience many of these effects. By scaling these up to human experience, we can begin to imagine the surreal consequences. Time slowing to a crawl, space flattening, radiation turning deadly, and the very perception of the universe transforming into something alien and unrecognizable. So, in this exploration, we will walk through the major consequences of traveling at or near the speed of light. We will see how Einstein's work shattered the Newtonian view of motion, why infinite energy would be required to reach the ultimate speed, how mass and time warp as velocity increases, what light itself experiences, and why the universe becomes hostile to any traveler attempting this impossible feat. And finally, we will ask the profound closing question. If the speed of light is forever out of reach, what does that mean for the future of human exploration? Does it lock us into our solar system, or does it hint at deeper loopholes in reality, like wormholes and warp drives, that may one day offer a backdoor? This journey is not about reaching a simple answer, but about uncovering the layers of mystery. Light speed is both a wall and a window that blocks our direct passage, and a window into the very essence of the universe. And as we peel back each layer, the story becomes stranger, more profound, and more humbling. Because in the end, the question of light speed travel isn't just about spaceships or technology. It's about what kind of universe we live in, and whether our dreams of transcending time and space align with the fabric of reality itself. Einstein's theory of relativity, formulated in the early 20th century, revolutionized our understanding of motion, space, and time, and it serves as the fundamental reason why traveling at the speed of light is considered physically impossible for any object with mass. Before Einstein, classical Newtonian mechanics suggested that speed was relative and additive, implying that in theory we could keep accelerating a spacecraft indefinitely and eventually surpass light itself. Relativity shattered that assumption by introducing the idea that the speed of light is not just a fast velocity, it is a cosmic speed limit built into the very geometry of space-time. The equations of special relativity make it clear that no object with mass can ever reach or exceed this limit, because the energy required to do so grows without bound. At the heart of this is the concept that as an object moves faster, its relativistic mass increases. Unlike the everyday experience of inertia we observe at low speeds, relativistic effects grow dramatically as velocity approaches the speed of light. This is expressed mathematically through the Lorentz factor, which measures how much time, length, and mass are distorted at high speeds. As you accelerate closer to light speed, this factor approaches infinity, and with it, the energy required to continue accelerating also approaches infinity. Simply put, the faster you go, the heavier you become, and the more energy you need to go even faster. At light speed itself, the equations demand infinite energy, a resource that is physically impossible to supply. The universe, it seems, has set a boundary that cannot be crossed. This limitation is not merely theoretical. Particle accelerators on Earth already give us a glimpse of relativistic effects in practice. Electrons and protons in accelerators can reach speeds exceedingly close to light, yet despite colossal energy inputs, they can never reach it. As particles approach light speed, tiny increments in velocity demand exponentially larger amounts of energy, demonstrating that the barrier is not technological, but fundamental. The speed of light acts as a natural boundary that preserves causality, preventing effects from happening before their causes, and keeping the universe's timeline consistent. If a massive object could reach or exceed light speed, these basic rules would break down, allowing paradoxes that physics is ill-equipped to handle, such as backward time travel or violations of energy conservation.
Furthermore, relativity shows that massless particles like photons, which do travel at light speed, behave fundamentally differently from anything with mass. Photons have no rest mass, so they can move at light speed without requiring infinite energy. Anything with mass, however, carries inertia, and inertia resists acceleration. The closer a massive object gets to the speed of light, the more the universe effectively pushes back against further acceleration. No matter how advanced technology becomes, the equations insist that light speed is forever unattainable for massive objects. It is not a matter of ingenuity or engineering. It is written into the very structure of space-time itself. This has profound implications for human ambition. It means that any interstellar journey we might imagine at light speed is doomed to remain in the realm of thought experiments. Rockets, engines, and propulsion systems, no matter how advanced, cannot break through this boundary. We can approach it, yes, but never cross it. And as we approach it, the consequences are no longer just abstract. They begin to warp reality itself. Time slows, distances shrink, and energy requirements soar. Einstein's insight tells us that the universe is not a playground where we can ignore the limits of physics. It is a finely tuned system with strict rules, and light speed is the ultimate speed limit that enforces order across space and time. As we delve deeper into the consequences of approaching the speed of light, the problem of energy becomes immediately apparent. According to relativity, the closer an object with mass gets to light speed, the more energy it requires to continue accelerating. This is not a linear relationship, it is exponential. At everyday speeds, pushing a car or plane slightly faster requires only a small increase in energy. But as velocity approaches the speed of light, every tiny increment demands vastly more energy than the last. The Lorentz factor, which grows without bound as you near light speed, mathematically illustrates this principle. When you plug in the numbers, the energy required to actually reach light speed becomes infinite. Infinite energy is not just beyond current technology, it is beyond the fundamental limits of the universe. There is no source, no matter how massive or powerful, capable of supplying it. This has concrete implications for any theoretical spacecraft. Even the most advanced propulsion systems we can imagine, antimatter engines, fusion drives, or hypothetical exotic energy sources, would encounter the same roadblock. As the ship accelerates, its effective mass increases, meaning that the force needed to continue accelerating grows relentlessly. Eventually, it reaches a point where adding more fuel or more energy yields almost no increase in velocity. This is not due to inefficiency or engineering limitations. It is a hard law dictated by spacetime. The universe itself resists our efforts to reach light speed, and it does so in a way that is mathematically precise. Every joule of energy propels us less than the previous one, approaching zero gain as we near the limit. Attempting to push beyond would be like trying to climb an infinitely steep hill. The summit is forever out of reach. Even on the subatomic scale, this principle manifests clearly. Particles accelerated to near light speeds in particle colliders require disproportionately enormous amounts of energy to inch closer to light speed. The Large Hadron Collider, for example, can propel protons to 99.9999% of light speed, but achieving the remaining fraction requires energy far beyond what we can generate on Earth. The paradox is striking. Particles can come incredibly close to light speed, yet the final step to reach it is completely unattainable. This demonstrates that infinite energy is not just a theoretical concern, it is a tangible barrier confirmed by experiments. The laws of physics do not allow us to cheat. They enforce the light speed boundary at every scale.
Moreover, this requirement for infinite energy is intimately connected to the concept of mass increase. As mass grows with velocity, so does the energy needed for further acceleration. This feedback loop becomes self-reinforcing. More speed demands more energy, which increases mass, which in turn demands even more energy. No propulsion system can escape this vicious cycle. Even if humanity discovered a form of energy more potent than all the stars in the galaxy combined, it would still be insufficient to push a massive object to the speed of light. The cosmic speed limit is not a technological challenge, but a fundamental law woven into the fabric of the universe. This principle also highlights a broader truth about our universe. It is inherently self-consistent. The infinite energy requirement is nature's way of preserving causality and preventing paradoxes that could arise from superluminal motion. By making light speed inaccessible to mass-bearing objects, the universe ensures that cause precedes effect and that energy conservation is never violated. It is a subtle, elegant enforcement of cosmic order. The dream of instant interstellar travel must confront this unyielding wall. Energy cannot be borrowed, created, or circumvented to cross it. The speed of light, in essence, is a law of the universe written in the language of energy itself, and it is absolute. As an object accelerates closer to the speed of light, one of the most profound and counterintuitive effects predicted by Einstein's theory of special relativity is the increase of its relativistic mass. In everyday life, we perceive mass as a constant property. A car, a person, or a planet has a fixed amount of matter that does not change as it moves. But at velocities approaching the speed of light, this assumption breaks down entirely. Relativity shows that mass is not an immutable quantity. It is intertwined with motion. The faster you move, the heavier you effectively become. This is not just a metaphorical statement. It is a precise physical reality encoded in the mathematics of space-time. Mathematically, the relationship is expressed through the Lorentz factor, represented as gamma. The Lorentz factor is defined as 1 divided by the square root of 1 minus v squared over c squared, where v is the velocity of the object and c is the speed of light. As velocity approaches c, the denominator of this expression approaches 0 and gamma approaches infinity. This means that relativistic mass, calculated as the rest mass multiplied by gamma, also approaches infinity. For practical purposes, this increase in mass has immediate and severe consequences. It requires more and more energy to achieve additional acceleration. The closer you get to light speed, the harder it becomes to push yourself any faster. Every attempt to increase velocity meets exponentially increasing resistance, a resistance that is literally built into the structure of the universe itself. To visualize this, imagine pushing a heavy object along the ground. At low speeds, your efforts result in relatively large changes in velocity. As the object becomes heavier, however, the same force produces smaller and smaller acceleration. Now imagine that your object does not just get heavier incrementally, but grows heavier at a rate that skyrockets as you near a universal speed limit. This is exactly what happens to objects moving at relativistic speeds. An electron, a spacecraft, or even a hypothetical human traveler would find that near light speed motion is like pushing against an invisible, ever-increasing wall. No matter how much energy you apply, the velocity gain diminishes, asymptotically approaching, but never reaching the speed of light. The effects of mass increase are not merely theoretical. They have been observed repeatedly in particle physics experiments. In particle accelerators, subatomic particles like protons and electrons are accelerated to velocities approaching light speed. Scientists have measured that as these particles move faster, their effective inertia increases in precise agreement with Einstein's predictions. The accelerators must supply exponentially greater amounts of energy to produce even minute increases in velocity. For instance, a proton might reach 99.99999% of light speed with tremendous energy input, yet reaching 100% of light speed is physically impossible because the energy required becomes infinite. The fact that relativistic mass increase is so rigorously confirmed experimentally gives us strong confidence in these predictions for larger objects, including any hypothetical spacecraft or astronaut. This mass increase has profound implications for acceleration. In Newtonian mechanics, acceleration is simply the result of force divided by mass. But when mass itself is not constant and grows with velocity, acceleration becomes far more complex. As the spacecraft accelerates, the growing mass requires progressively greater force to continue increasing speed. Even if humanity developed propulsion systems orders of magnitude beyond our current capabilities, the relativistic feedback loop would still enforce a strict limit. At relativistic speeds, adding more fuel or more thrust yields diminishing returns. The universe ensures that the light barrier remains intact, making it a universal speed governor that applies equally to subatomic particles, spacecraft, or any object with mass. The relativistic mass increase also interacts in dramatic ways with other effects predicted by Einstein, especially time dilation and length contraction. As mass grows and energy requirements soar, time for the moving observer begins to slow relative to stationary observers. This is not a separate phenomenon, but a consequence of the same relativistic framework.
In fact, the mass increase, time dilation, and length contraction are deeply intertwined, forming a consistent and self-reinforcing set of rules governing near-light-speed motion. The closer you approach the cosmic speed limit, the more reality itself seems to bend. The universe begins to behave in ways that defy intuition. Distances shrink, time stretches, and the concept of what it means to move, to experience energy, and to age becomes dramatically different from everyday life. For humans, the consequences of mass increase are particularly severe. A spacecraft designed to approach light speed would require fuel and propulsion systems of unimaginable scale, simply to achieve velocities even a fraction below c. The effective mass of the craft would increase so rapidly that it could exceed planetary or even stellar mass equivalents by the time it reached 99.999% of light speed, not because the spacecraft physically gained matter, but because of relativistic effects. The energy requirements to push such a heavier vehicle increase correspondingly, creating a loop where acceleration becomes exponentially more difficult with every fraction of light speed gained. It is a vivid demonstration of how relativity imposes not just theoretical but practical limits on travel through space. This mass increase also impacts the safety of any potential travelers. At near light speeds, the kinetic energy of even a single particle colliding with the spacecraft becomes colossal due to the effective increase in mass. A tiny speck of cosmic dust, harmless at conventional velocities, could impact with the force equivalent to a nuclear explosion. The very act of traveling close to light speed transforms the universe into a dangerous, energetic environment where collisions are magnified by relativistic mass effects. This makes near light speed travel not only energetically prohibitive, but also hazardous, reinforcing the idea that light speed motion is not merely a technological hurdle, but a fundamental constraint imposed by the structure of reality. Moreover, the concept of mass increase emphasizes the difference between approaching light speed and reaching light speed. As long as an object has mass, it can theoretically accelerate toward light speed. But the closer it gets, the more extreme the energy demands become. Unlike massless particles like photons, which naturally travel at light speed, any massive object will always asymptotically approach but never touch this limit. The universe is structured in such a way that light speed is a boundary, a horizon that defines the ultimate limit of motion. Mass increase is the mechanism by which this limit is enforced, linking velocity, energy, and inertia into a single, consistent framework that leaves no room for exceptions. Understanding mass increase also forces us to reconsider our intuitive notions of motion. We tend to think of speed as a simple measure of how fast something is moving through space. Relativity teaches us that speed is deeply connected to the fabric of space-time itself. As you move faster, your mass grows, your experience of time changes, and distances contract. These effects are not arbitrary. They are all mathematically interdependent consequences of approaching the ultimate speed limit. Mass increase, in particular, ensures that the laws of physics remain self-consistent. Without it, light speed could theoretically be surpassed, leading to causal paradoxes and violations of energy conservation. In this sense, mass increase is not merely an inconvenience, it is a fundamental safeguard of reality. In short, as velocity increases toward the speed of light, mass increases in a way that makes further acceleration progressively harder. The more you try to go faster, the heavier you become, and the more energy is required to continue accelerating. This feedback loop, confirmed by experiment and predicted by relativity, ensures that no massive object can ever reach light speed. It also reshapes our understanding of motion, energy, and the structure of the universe. Mass increase transforms the dream of light speed travel into a series of near impossible hurdles, where energy demands soar, time dilates, and even the simplest interactions with the cosmos become extraordinarily violent. It is both a barrier and a profound window into the way reality is fundamentally constructed,
illustrating how the universe enforces its ultimate speed limit at every scale. One of the most extraordinary and mind-bending consequences of Einstein's theory of relativity is time dilation, the phenomenon in which time itself does not flow at the same rate for all observers, but instead depends on their relative motion. At everyday speeds, this effect is so minuscule that it is imperceptible. Our clocks, our bodies, and our daily lives tick away at seemingly universal rates. But as soon as we enter the realm of relativistic speeds, velocities approaching the speed of light, time begins to bend in ways that defy intuition. For the traveler hurtling through space at near light speed, seconds, minutes, and hours continue to feel normal, yet to an outside observer watching from a stationary frame, those same seconds stretch into hours, years, or even centuries. Time slows dramatically for the traveler compared to the universe left behind, a distortion of reality that is as fascinating as it is unsettling. The mechanism behind time dilation lies in the Lorentz transformations, the mathematical framework that replaces the old Newtonian view of absolute time. In Einstein's universe, time is not an independent backdrop against which events unfold. It is inseparably tied to space, forming the four-dimensional fabric of space-time. When an object moves very quickly through space, its progression through time is altered. The faster the motion, the slower the rate at which its internal processes, heartbeat, thought, biological aging, the ticking of a clock, appear to proceed compared to an observer at rest. This is not an illusion, not a trick of perception, but a genuine alteration in the passage of time itself. To see how striking this becomes, imagine a spaceship accelerating to 90% of the speed of light. On board, the crew members experience time normally. Their watches tick at the usual pace, conversations flow naturally, and they feel no difference in the passage of moments. But to an observer on Earth, watching the ship with a powerful telescope, everything inside the ship seems to slow down. A clock that ticks once per second inside the ship may appear to tick only once every 2 seconds from Earth's perspective. Push the velocity to 99% of the speed of light, and the effect intensifies. What feels like 1 hour on the ship could correspond to 7 hours on Earth. At 99.999% of light speed, the disparity grows more extreme still, with years passing on Earth, while the travelers experience mere days or even hours. This leads to one of the most famous thought experiments in relativity, the twin paradox. Suppose one twin boards a spacecraft that travels at near light speed for what feels like a few years, while the other remains on Earth. When the traveling twin returns, they will find that their sibling has aged decades, perhaps even centuries, while they themselves have aged only a fraction of that time. This scenario, while paradoxical at first glance, is a real consequence of time dilation and has been confirmed experimentally, not with humans, but with highly accurate atomic clocks. When synchronized atomic clocks are flown on airplanes or satellites, and then compared with identical clocks on the ground, tiny but measurable differences in elapsed time are observed, exactly as relativity predicts. The effect may be tiny at low speeds, but it is real, and at relativistic velocities, it becomes enormous. For the traveler, this slowing of time offers both a tantalizing promise and a sobering cost. On the one hand, near light speed travel could allow astronauts to reach distant stars within their own lifetimes, because their personal time is stretched out far less than the time experienced by the universe around them. A voyage to a star system dozens of light years away might feel like a few years on board, while centuries pass on Earth. In this sense, time dilation becomes a kind of one-way ticket to the future. Traveling close to light speed is a method of time travel, allowing individuals to leap forward in cosmic history. Yet this same effect also isolates the traveler, cutting them off from the timeline they once knew. By the time they return, the world they left behind may be unrecognizable, its people long gone, its civilizations transformed. The traveler escapes time's grasp only to lose everything familiar to it. Time dilation, also reveals the profound relativity of time itself. To the traveler, nothing feels unusual. Their watch ticks normally, their heart beats at its regular rhythm, and their perception of duration remains unchanged. But to everyone outside, the traveler is living in slow motion. Which perspective is correct? In relativity, both are correct. Time does not flow universally, but depends on the frame of reference. Each observer experiences their own reality consistently, yet when these realities are compared, they diverge in ways that highlight the flexibility of space-time itself. This is one of the most radical departures from Newtonian physics, where time was thought to be absolute, unchanging, and universal. Relativity shows that time is elastic, stretching and compressing depending on motion and gravity. The concept becomes even more extreme as velocity creeps ever closer to the speed of light. If a spaceship could somehow reach 99.9999% of light speed, the traveler's time would slow to such an extent that for every year experienced on board, thousands or even millions of years could pass for outside observers. The ship could launch, travel for a few years of the crew's subjective time, and return to find Earth unimaginably changed, perhaps unrecognizable, with new continents, evolved species, or entirely different civilizations. From the traveler's perspective, the journey felt short and manageable, but from Earth's perspective, it was a leap through epochs of history. Time dilation thus becomes not only a physical effect, but a philosophical and emotional one, redefining our relationship with the flow of time and with the very concept of continuity. This phenomenon is not just a curiosity, it is deeply embedded in modern science and technology. GPS satellites, for example, orbit Earth at high velocities and experience both gravitational and motion-induced time dilation. Engineers must account for these relativistic effects. Otherwise, the system's clocks would drift and navigation would quickly become inaccurate. The fact that our everyday devices rely on corrections for relativistic time dilation underscores its reality. Relativity is not a distant, abstract theory. It governs how time itself unfolds, even for the technologies we use daily. Ultimately, time dilation illustrates the profound interconnectedness of space, time, and motion. As we accelerate closer to the speed of light, time slows, not because of mechanical processes or external influence, but because space-time itself reshapes around motion. This is a fundamental law of the universe, confirmed by observation and experiment. The dream of light-speed travel is therefore not just about covering distances quickly. It is about entering a realm where time itself becomes malleable, where a traveler can leap centuries into the future in the span of a heartbeat. Yet the very laws that make this possible also make it tragic, severing the traveler from their own era and ensuring that near-light-speed journeys are less about exploration and more about irreversible exile into the future. If we push the thought experiment even further and imagine a scenario that defies physics, a massive object somehow reaching the speed of light, the consequences become truly surreal. According to Einstein's equations, as velocity approaches light speed, time dilation grows without bound. Time slows for the traveler relative to the outside universe, stretching seconds into years, hours into centuries. But at the exact speed of light, this dilation would become absolute. Time for the traveler would come to a complete standstill. From their perspective, the passage of time would vanish entirely. Clocks would freeze, biological processes would halt, and the very sense of change would evaporate. Every event, every motion, every heartbeat would cease to progress. The traveler would be locked in a timeless state, suspended in the instant of their motion. It is not simply that they would experience time differently. It is that, from their own perspective, time itself would no longer exist. This extreme case illustrates the absolute nature of light speed as a boundary. At light speed, the familiar concepts of before and after, past and future, would lose all meaning. The universe, in essence, would be a frozen tableau from the traveler's viewpoint.
Distances would collapse to zero. Light from the cosmos would no longer propagate in a useful way, and all movement relative to the traveler would become meaningless. It is as if the universe itself condenses into an eternal instant. For a photon, which naturally travels at light speed, this is precisely the reality. It is emitted and absorbed without experiencing any passage of time, even across vast cosmic distances. For anything with mass, however, this scenario is purely hypothetical, because the infinite energy required to reach light speed prevents it from ever occurring. Yet considering this extreme highlights how radically relativity transforms our understanding of motion and time. The implications for human perception are profound. We tend to experience time as a continuous flow, marked by memory, anticipation, and change. Reaching light speed would eliminate all of these markers. Without time, experience itself becomes impossible. There would be no subjective now, because the notion of now relies on the progression of moments. From the traveler's standpoint, the journey would be instantaneous, regardless of how far or fast they were moving. A voyage to the edge of the observable universe, which would take billions of years for outside observers, would be experienced as a single, timeless instant. While this may seem like the ultimate form of speed, it paradoxically removes all possibility of perceiving or interacting with the universe in a meaningful way. The faster you go, the more time stretches, and at light speed, the stretching becomes infinite, collapsing your experience of existence into stillness.
This thought experiment also underscores the distinction between theory and reality. While relativity predicts that time stops at light speed for massless particles, any object with mass cannot reach this velocity because of the infinite energy requirement. Thus, the extreme case is a conceptual tool rather than a physically achievable situation. Yet it serves as a powerful illustration of the boundaries imposed by the universe. By imagining what would happen if we could breach these limits, we gain insight into how space-time is structured and why light speed is not just a fast pace, but an ultimate barrier that governs causality, energy, and the very flow of time. In this frozen state, the laws of physics that define change and motion no longer function as we understand them. The traveler would exist in a unique, paradoxical condition where distance, duration, and experience dissolve simultaneously. Moreover, this extreme scenario invites philosophical reflection. If time stops for the traveler, then the universe itself, relative to them, becomes a single, unchanging entity. The past, present, and future converge into a single point, collapsing the narrative of events. For humans, whose consciousness is inherently temporal, such a state is unimaginable. Yet relativity suggests that for massless entities like photons, this is the default reality. Considering the extreme case forces us to confront how deeply our experience of reality is tied to the flow of time. It is not merely a convenience, it is a structural aspect of existence. Time provides causality, sequence, and meaning. Without it, there is motion, but there is no experience, no change, no interaction, just the frozen geometry of the universe. Even the cosmic landscape itself would transform from the traveler's perspective. The distances between stars and galaxies would contract dramatically, collapsing along the direction of travel into an almost singular plane. Light that defines vision would behave differently. Forward-facing light would be impossible to catch, while light from behind would compress infinitely, creating distortions beyond comprehension. The traveler at light speed would be surrounded by a universe that is no longer extended in the conventional sense, but compressed into a timeless, dimensionally altered state. In effect, motion at light speed does not just make you faster, it fundamentally rewrites the rules of perception, erasing the continuum of space and time that anchors all experience. Ultimately, the extreme case of light-speed travel serves as a stark reminder of the limits imposed by relativity. It demonstrates that the cosmic speed limit is not merely about velocity, but about the deeper structure of reality,
Energy, mass, time, and space are all interlinked in a web that forbids exceeding light speed. The dramatic slowing and ultimate cessation of time show that attempting to reach this speed would not produce adventure or exploration, but a paradoxical imprisonment in a single, eternal instant. It is a frontier of thought rather than a frontier of travel, revealing the counterintuitive, profound, and sometimes unsettling nature of the universe we inhabit. As you begin to approach the realm of light speed, reality itself seems to twist around you. One of the strangest and most counterintuitive predictions of Einstein's special relativity is something called length contraction. To someone traveling near light speed, the very fabric of space ahead of them does not appear the same as it does to an observer standing still. Instead, distances in the direction of travel begin to shrink. If you were hurtling forward in a spaceship at a significant fraction of light speed, the stars that lie ahead wouldn't seem impossibly far away anymore. They'd appear squeezed together, as though the cosmos itself was folding to shorten your path. Roads that once stretched endlessly now seem compressed, as if the journey is being warped by your speed. This isn't an illusion or a trick of perception. It's a fundamental aspect of how space and time adjust to preserve the cosmic speed limit of light. The closer you get to light speed, the more extreme this contraction becomes. Imagine heading toward a distant galaxy millions of light years away. To someone observing from Earth, the journey would still span millions of years, even if you traveled at an incredible pace, just shy of light speed. But from your perspective inside the ship, that same distance may not feel like millions of light years at all. It could appear drastically reduced, compressed into something you could cross within your own lifetime. Space itself bends to allow you the possibility of reaching a destination that would otherwise remain eternally out of reach. What was once vast beyond comprehension begins to collapse into something more manageable, though only for you, the traveler.
This phenomenon has staggering implications. It means that the universe doesn't look the same for everyone. Space isn't a fixed, rigid stage on which events unfold equally for all observers. Instead, it is flexible, stretching or shrinking, depending on the relative speed at which you move. At normal human scales, we never notice this because our speeds are so small compared to light. But as you push into relativistic realms, everyday rules collapse, and the universe reveals a hidden side. The spaceship's nose points into a corridor of stars that appear drawn closer, stacked tightly together, as though the entire cosmic fabric is rushing in to meet you. Yet this shrinking of space is a double-edged sword. While it suggests that journeys across the stars could, in theory, be made to feel shorter for the traveler, it doesn't erase the fact that to those left behind, the trip still takes the vast amount of time it should. You may feel as though you have leapt across interstellar gulfs in a flash, but to the universe outside, you've still obeyed the unyielding laws of relativity. Both perspectives are true at the same time, each valid within its own frame of reference, even though they seem to contradict each other. This paradox-like quality lies at the heart of relativity's brilliance. It doesn't change the underlying laws, but it changes how those laws manifest depending on who's observing. The closer you get to the ultimate speed limit, the more intense this contraction becomes. In the theoretical limit of reaching the exact speed of light, the distance in front of you would collapse entirely. Space itself, in the direction you're moving, would shrink down to zero. That means that if you could somehow ride alongside a beam of light, from your perspective, there would be no distance left to cross at all. The universe would flatten to nothingness in the path ahead. Of course, such a journey is forbidden for objects with mass, but the thought experiment reveals just how strange the rules of reality become when you dance near light's domain. Length contraction, time dilation, and mass increase are all interconnected, woven together into the fabric of relativity. Space shrinks, time slows, and mass grows heavier, all conspiring together to protect the cosmic boundary of light speed. What you gain in contracted distance, you lose in the slowing of your personal time compared to the rest of the universe. To the traveler, the stars draw close. To those watching, the traveler drifts slowly through the void over unimaginable spans. Reality bends itself into different shapes, each consistent, each true, but radically different depending on where you stand and how fast you move. And so, as you imagine yourself racing toward the cosmic speed limit, the journey ceases to be just a matter of covering ground. It becomes a transformation of existence itself. The universe ahead doesn't stay fixed. It folds, shrinks, and compresses as if beckoning you forward. To step closer to light speed is to peel back the everyday mask of reality and glimpse the elastic, malleable nature of the cosmos, where distance and time are not constants, but variables that shift depending on the speed at which you dare to travel. As you push ever closer to the speed of light, the visual experience of the universe undergoes a transformation as dramatic as any in physics. The very way light reaches your eyes changes, and with it, the cosmos appears to compress into a startling and surreal spectacle. At everyday speeds, stars and galaxies are distinct points of light scattered across a vast, three-dimensional expanse. But as your velocity approaches the relativistic domain, these points begin to smear and shift, converging into streaks and blurs that defy normal perception. This is because of a phenomenon known as the relativistic aberration of light, which effectively bends the paths of photons in the direction of your motion. To you, traveling at an extreme fraction of light speed, the universe itself seems to collapse forward, concentrating light into a narrow cone ahead of you, and the vast distances between galaxies appear dramatically reduced. The effect is not subtle. Stars that once twinkled in familiar constellations stretch into long trails of light, aligned along the direction of your trajectory. Entire galaxies, separated by millions of light years when observed from Earth, begin to appear compressed, overlapping, and even merging visually. The universe that once seemed infinite and sprawling now feels like a tunnel of brightness, a cosmic kaleidoscope in motion. The light from objects behind you is progressively left behind, barely reaching your eyes, while the light from everything ahead is concentrated into an increasingly narrow and intense point. The further you accelerate, the more severe this visual contraction becomes, until at the extreme limit, the stars ahead of you would appear to converge into an almost singular flash of light, a brilliant, blinding corridor stretching infinitely forward. This blurring is compounded by the Doppler effect at relativistic speeds. Light from stars in front of you shifts toward higher frequencies, moving through the visible spectrum and into ultraviolet, X-rays, and eventually gamma rays. The wavelengths of photons are compressed as your velocity increases, so what was once familiar starlight becomes a dangerous torrent of high-energy radiation. Not only do distances contract visually, but the very color and intensity of the universe transforms. From a visual standpoint, motion near light speed is not just fast. It is a radical rewriting of the universe's appearance, a distortion so profound that it is nearly impossible for the human brain to process without imagination. To the traveler, this creates a paradoxical mixture of intimacy and abstraction. Vast stretches of intergalactic space, which would take millions or billions of years to cross at normal speeds, seem compressed into visual proximity. Galaxies that should be eternally distant appear close enough to be almost tangible. At the same time, this compression is deceptive. Distances are not truly shrinking in a Newtonian sense. They are contracted only relative to your frame of reference. The light from these galaxies, bent and warped by your immense velocity, creates a perception of speed and proximity that is profoundly misleading. You might feel as though you are moving through a dense, vibrant cosmos, when in reality you are still separated from distant galaxies by colossal stretches of space. The effect also has implications for navigation and observation. At near light speed, the universe appears to collapse into a visual cone directly ahead of you, while the rest of the cosmos seems to fade into darkness. Your field of view narrows, and objects that would normally be on the periphery
are pushed toward the center of your vision. This concentration of light is a natural consequence of special relativity. Photons traveling from the sides are seen as coming from a direction closer to your trajectory, creating a forward-focused tunnel of light. The visual panorama of the universe no longer obeys the familiar rules of geometry or perspective. It is as though reality itself has been funneled through a relativistic lens, emphasizing the forward direction of motion while compressing the immensity of space into a rapidly contracting view. Beyond the visual spectacle, there is also a temporal distortion. Light from distant stars that reaches you in this high-speed frame is not merely compressed spatially, it is also compressed in time. Photons that would normally arrive over years or millennia arrive in rapid succession, as if the universe is playing a cosmic fast-forward. To the traveler, the sky might appear to shift almost instantaneously, galaxies flashing past as their light converges into the tunnel of motion. This creates an eerie sense of temporal acceleration, where the flow of the universe outside seems to condense into a continuous, overlapping instant. The more closely you approach the speed of light, the more extreme this temporal compression becomes, reinforcing the idea that relativistic travel is as much about warping perception as it is about covering distance. These effects combine to create an almost alien perception of reality. The universe, vast and stable at low speeds, becomes dynamic, compressed, and visually distorted. Light from all directions is pulled into a forward-focused spectacle. Time and space seem to overlap, and the familiar night sky transforms into a surreal blur of converging galaxies. It is an experience that underscores the counterintuitive nature of relativity. Even the most fundamental aspects of reality, distance, time, and light, cannot be assumed to remain fixed when approached at the ultimate cosmic velocities. In essence, to travel near light speed is to witness the universe in a flash. The vast separations that define the cosmos shrink visually, stars and galaxies blur into overlapping streaks, and the familiar geometry of space seems to dissolve. The cosmos becomes less a fixed expanse and more a tunnel of light and motion, a constantly shifting vista that compresses time, space, and perception itself. Yet this remarkable visual transformation comes with a warning. The same contraction that makes galaxies appear closer also brings with it extreme energy, radiation, and relativistic hazards, emphasizing that the dream of near light speed travel is both awe-inspiring and profoundly dangerous. As you approach velocities close to the speed of light, another invisible yet deadly phenomenon begins to dominate your environment: the transformation of background radiation into an energetic storm. The universe is not empty. It is filled with the cosmic microwave background, a faint afterglow of the Big Bang that bathes space with uniform microwave radiation. At rest, this radiation is harmless, a barely perceptible whisper of energy. But when you start moving at relativistic speeds, the story changes dramatically. The motion of your spacecraft relative to this background creates a relativistic Doppler effect, shifting the wavelength of incoming photons toward higher energies, a process known as blue shifting. To you, the harmless microwaves transform into intensely energetic photons, gradually moving through infrared, visible light, ultraviolet, X-rays, and ultimately into the deadly realm of gamma rays. The faster you go, the more extreme this blue shifting becomes. At a fraction of light speed, the cosmic microwave background begins to appear as ordinary light, perhaps glowing slightly in your instruments. Push closer to 99% of light speed, and the background radiation is no longer just bright. It is penetrating, ionizing, and destructive. Every photon striking your spacecraft carries exponentially more energy as velocity increases. At the extreme limits of near light speed travel, the cosmic microwave background would effectively become a relentless barrage of gamma radiation. For any human traveler without extraordinary shielding, exposure would be instantly fatal. The very fabric of the universe becomes hostile, not through obstacles or collisions,
but through the fundamental interaction of your motion with the omnipresent energy of space itself. This effect highlights an often overlooked aspect of relativistic travel. It's not just distance, time, or acceleration that imposes limits. The environment itself becomes more extreme and dangerous as velocity increases. While we often think of space as a vacuum, a safe void through which one can traverse unimpeded, relativity shows that motion relative to the cosmos transforms even the emptiest regions into lethal terrain. The cosmic microwave background, essentially frozen and harmless at rest, is weaponized by your speed. Every molecule, every photon, every quantum of radiation is shifted into higher energy modes, bombarding your ship and increasing the difficulty of surviving or even remaining intact during near light speed travel. This radiation shift is a natural consequence of how electromagnetic waves behave under relativistic motion. Photons approaching from the direction of travel are compressed into higher frequencies, carrying more momentum and more energy per particle. Those from behind are redshifted, stretched to longer wavelengths, losing energy but also failing to illuminate the path ahead. This asymmetry creates a deadly forward-facing beam of energy, like a continuous laser from the very cosmos, aligned with your trajectory. The faster you go, the narrower and more intense this beam becomes, concentrating the danger directly in front of you. It is not something that could be mitigated simply with conventional shielding. The energies involved at extreme velocities surpass even the protective capacities of dense, exotic materials. The implications for any hypothetical traveler are profound. Even if you solved the energy problem, overcame mass increase, and survived the relativistic stresses on your body and spacecraft, the environment of space itself becomes a formidable adversary. Blue-shifted radiation at near light speed is not merely uncomfortable, it is fundamentally destructive, capable of ionizing atoms, breaking molecular bonds, and instantly obliterating unprotected tissue. The universe, normally serene and empty from a stationary perspective, becomes a storm of energetic particles, a relentless gauntlet fired by your own velocity. Every second of travel becomes not just a matter of distance, but a contest against the intrinsic radiation of the cosmos. From a physics perspective, this shift also underscores the inseparable link between motion and observation. Light, radiation, and energy are not absolute. They are dependent on relative velocity. The universe reacts to motion, reshaping the energy spectrum of photons in ways that are entirely predictable mathematically, but terrifyingly extreme in practice. This means that the cosmic environment is not merely a static backdrop, it is dynamic, and your interaction with it changes as you move. The faster you go, the more the universe itself seems to fight back, enforcing the limits of speed through energy and radiation. Even if acceleration was somehow achieved, the blue-shifted bombardment of gamma rays stands as a natural boundary, a physical manifestation of the cosmos's enforcement of relativistic laws. This effect also emphasizes the contrast between theory and feasibility. While relativity allows us to calculate exactly what would happen to background radiation at near-light speeds, the practical consequences for life, technology, and exploration are stark. You cannot simply speed through the universe without consequences. The cosmos itself imposes its own hazard, a radiation wall that grows more intense the closer you get to the speed of light. The elegant equations of Einstein describe what occurs in a frame of reference, but they also warn us that certain velocities are not just impractical, they are fatal under ordinary conditions. In this sense, the blue-shifted cosmic microwave background is one of many natural checks that prevent us from experiencing light-speed travel directly. As you consider the interplay of time dilation, mass increase, length contraction, and now the radiation environment, it becomes clear that near-light speed travel is far more than a matter of technology. It is a confrontation with the fundamental structure of reality. The cosmic microwave background, a relic of the early universe, becomes transformed into a weapon of the universe itself. striking anyone bold enough to approach the ultimate speed limit. The experience of the universe at relativistic speeds is therefore not only visually and temporally extraordinary, but also physically hostile, revealing that our dream of reaching or surpassing light speed is constrained by every aspect of space-time and energy. The universe, elegant and beautiful at rest, becomes a violent and alien place when viewed from the frame of a near light-speed traveler, a reminder that the cosmos enforces its limits in ways both subtle and lethal. As we continue to explore the relativistic frontier, one concept becomes absolutely central: the so-called light barrier. It is often described as an invisible wall that nothing with mass can penetrate, a universal speed limit baked into the very laws of physics. Unlike traditional barriers, it is not a material obstruction. It is an intrinsic property of space-time itself. At first glance, the idea may seem like a simple speed limit, like a speedometer on a cosmic scale, but the reality is far more profound. The light barrier is not just a limit on velocity. It is a point at which our classical notions of physics begin to unravel. Beyond it, the familiar rules of mass, time, energy, and distance no longer apply in any conventional sense. To reach it would mean pushing the universe itself to a state it fundamentally cannot sustain. The impossibility of crossing this barrier is intimately tied to the phenomena we've already discussed. Mass increases without bound as you approach the speed of light. Time dilation stretches infinitely, and distances contract to vanishing points. All of these are consequences of the Lorentz factor, which mathematically governs motion in special relativity. At light speed, this factor becomes infinite, mass approaches infinity, time for the traveler stops completely, and length along the direction of motion collapses to zero. The universe is signaling in no uncertain terms that the speed of light is not merely a goalpost, it is a boundary that defines what can and cannot exist physically. Any attempt to cross it is not just technically difficult, it is fundamentally incompatible with the structure of reality. It is crucial to understand that the light barrier is not merely about acceleration. One might imagine applying enough thrust, enough energy, to break through this limit. But relativity tells us that no finite quantity of energy is sufficient. As velocity approaches light speed, the energy required to achieve further acceleration grows without bound. To move an object with mass to light speed would require infinite energy, which is not just impractical. It is literally impossible within the laws of physics. The barrier is self-enforcing. It exists not because of technological shortcomings, but because the universe itself forbids such motion. In this sense, the light barrier is less an obstacle to be overcome and more a fundamental property of spacetime, an immutable limit imposed by the relationship between energy, mass, and velocity. For objects with mass, the experience of moving at light speed is also impossible. Everything we understand about motion presupposes a progression through time and space, yet at light speed, both of these dimensions behave in ways that mass cannot accommodate. Time halts entirely, space contracts to zero in the direction of motion, and mass becomes infinite. To a hypothetical traveler, these conditions create a paradox. Motion requires time and energy, yet both are either unavailable or infinite. The physical laws break down precisely because the assumptions underpinning them, finite mass, finite energy, measurable time, and measurable distance, can no longer hold. Unlike photons, which are massless and naturally traverse the cosmos at light speed without violating these constraints, anything with mass is fundamentally excluded from this realm. This also explains a common misconception: the idea that reaching light speed would allow a traveler to instantly cross the universe. While relativistic effects such as length contraction and time dilation suggest that distances shrink and personal time slows, these effects are always relative to your frame of reference. The universe never actually allows mass to achieve true light-speed motion. The experiences suggested by theory, such as instantaneous travel or frozen time, are bound by the impossibility of reaching the speed itself. In other words,
you can get arbitrarily close to light speed and experience all the distortions it entails, but the actual crossing of the light barrier remains forever beyond reach. The effects you witness are extreme, but they are always finite and achievable only as limits approached asymptotically, not as attainable realities. The barrier is also self-consistent with the observations of outside observers. No matter how fast a massive object travels, it will always appear to approach light speed asymptotically, never actually reaching it. From the frame of an observer at rest, the object slows relative to their expectation as it nears the universal limit, approaching a state that seems almost frozen in motion. The laws of physics enforce this at every level, making light speed an unattainable horizon from both the travelers and the external observer's perspectives. This ensures that causality, the sequence of cause and effect, is preserved, and that the fundamental structure of the universe remains coherent. If mass could reach or exceed light speed, paradoxes would arise, threatening the integrity of space-time itself. In addition to preserving causality, the light barrier serves as a natural regulator for energy and momentum in the universe. By forbidding mass from attaining light speed, the cosmos ensures that infinite energies do not exist in a physical form, that matter retains finite mass, and that interactions remain predictable. It is a subtle but profound reminder that the laws of nature are deeply self-regulating. Attempts to bypass this barrier, whether through raw propulsion or theoretical exploits, run up against these fundamental constraints. Mass, time, energy, and space are all interlinked in a system that simply cannot sustain light-speed travel for anything with mass. The light barrier thus reveals the interplay between possibility and impossibility in the cosmos. It is not merely a technical or engineering challenge. It is a principle embedded in the structure of reality. Everything we have explored, mass increase, infinite energy requirements, time dilation, length contraction, and the visual distortions of the universe, converges on this singular truth. The speed of light is an absolute limit for any object with mass. Any attempt to experience motion at light speed is inherently blocked by the fabric of space-time, and physics breaks down in precisely the ways that enforce this prohibition. In this sense, the light barrier is both a boundary and a guidepost, showing us the edges of what is physically possible and illuminating the astonishing ways in which the universe maintains its own consistency. From the viewpoint of an outside observer, the situation looks very different than it feels to the traveler. As you accelerate closer and closer to the speed of light, your own perspective would suggest you're going faster and covering vast distances in less time. But to anyone watching from the outside, you would never actually hit light speed. Instead, they would see your velocity inch closer to it, but always fall short. Each burst of energy applied to accelerate you would have a smaller and smaller effect, like pouring water into a bottomless well. Observers would measure your clock ticking more slowly with each increment of speed, your movements stretching out in time. From their perspective, it would look as if you were caught in a kind of cosmic slowdown, struggling harder and harder against the speed limit of the universe. They wouldn't see you vanishing into a blur or instantly darting across the galaxy. Instead, they would witness your acceleration tapering off, approaching light speed asymptotically, meaning you get closer but never actually arrive. Imagine a graph where your speed rises steeply at first, but then the line begins to flatten as it nears the ceiling of light speed. No matter how much energy is poured in, the line never touches that ceiling. That is how relativity describes your journey from the outside frame. It's not that the engines fail or your effort ceases, but that the very fabric of space-time refuses to allow mass-bearing objects to achieve that ultimate velocity. Another strange aspect is that to the outside observer, the light you emit, whether from your ship or even from your body, would start to stretch into longer and longer wavelengths the faster you go. It would drift toward the red end of the spectrum in a process called redshift. As you approach the speed of light, the redshift becomes extreme. Eventually, you might appear to fade out of view entirely,
not because you're gone, but because the wavelengths of light are stretched beyond the range of detection. So from their perspective, you wouldn't suddenly streak away at light speed. You'd simply dim, stretch, and seem to freeze in time as your velocity pushed against the cosmic barrier. Even communication would break down. If you tried to send signals back, your messages would arrive more and more delayed, stretched by time dilation. To the observer, your words, your movements, your very existence would appear to slow until, at the very edge of light speed, you would look like you had frozen entirely. They'd never witness you passing that boundary. This effect is not just theoretical, it's deeply embedded in the equations of relativity and consistent with experiments involving particles in accelerators. Physicists have pushed particles like electrons to astonishingly close to light speed, but they always obey this rule. To the outside frame, they never truly touch light speed. This creates a paradox of perception. From your perspective, you might feel like you're moving faster, time shrinking around you, distances collapsing, galaxies whipping by. But to anyone outside, it would look like you're locked in a slow-motion struggle against an invisible wall, trapped just below the ultimate limit. This disconnect between internal and external viewpoints is one of the most fascinating and puzzling outcomes of relativity. It means that the journey to light speed isn't just about physics, it's also about perspective. And no matter how advanced our technology becomes, the outside universe will always see our attempts to reach light speed as a chase we can never quite finish. For light itself, the story takes an even stranger twist. Imagine photons, the tiny packets of light that stream across the cosmos. They have no rest mass, and because of this, they are not bound by the same physical rules that govern us. In our universe, they move at the ultimate speed limit, the speed of light itself. But here's the baffling part. From the perspective of a photon, time doesn't exist at all. To us, light may take billions of years to cross the universe, but for the photon, that journey is completed in what is essentially no time. There's no ticking clock, no progression of moments, no before and after. The instant a photon is emitted, say, from the surface of a distant star, and the instant it is absorbed, perhaps by your eye or a telescope on Earth, are the same event from the photon's point of view. Distance collapses, time collapses, and reality itself seems to fold into a single, timeless interaction. This challenges how we even think about existence. For everything we know, our lives and the cosmos are built on sequences of events, one moment leading to the next, but for light, that structure disappears. It exists outside of what we would call a timeline. If photons could speak, they might tell us that concepts like how long or how far are meaningless because their experience is not strung together by time in the way ours is. They would only know an eternal now. And yet, despite that, it is photons that allow us to see the past. When we gaze at distant galaxies, we are looking at light that set out billions of years ago, long before humans existed, long before Earth itself formed. We see those ancient signals stretched across time, but the photons carrying them didn't experience the weight. It's one of the deepest paradoxes in physics. The same particle that shows us the universe's age and distance doesn't experience either. If we try to imagine what it's like to be light, we hit a wall in our understanding. Because we, as beings with mass, are forever tied to the flow of time, we can't ever fully grasp what it means to exist outside of it. Yet light, indifferent to the very structure of time, continues racing across the universe, stitching together the fabric of reality, while never once experiencing the journey. From your own perspective, traveling at light speed would erase the flow of time completely. Imagine being locked into a reality where the second hand of a clock never ticks, where your heartbeat never echoes, where your thoughts never move forward. In this strange frozen state, time as you know it ceases to exist. Every moment you've ever known relies on the passing of seconds, but at light speed, those seconds would no longer unfold.
It's as if your entire existence becomes a single instant, stretched across eternity, a paradox of living, yet never moving forward in the timeline of the universe. You would feel as though you are outside of history, detached from the flow that governs everything else. But this isn't just some abstract science fiction scenario. It's the direct outcome of Einstein's relativity. According to relativity, as you accelerate closer and closer to the speed of light, time slows relative to outside observers. That slowing continues until, hypothetically, at the very moment you reach light speed, the rate of time from your frame hits zero. You would never experience the future because, from your perspective, it simply doesn't exist. To someone watching from afar, they would still see you moving, though never reaching the barrier. But for you, consciousness itself would be trapped in an eternal present. This state is beyond what human minds are built to truly comprehend, because everything we know, our memories, our choices, our sense of self, depends on time moving forward. If you were frozen in time, your brain could not form new thoughts, because thought itself requires progression. You couldn't make a decision, because decisions require a before and an after. It's almost as if your identity would be suspended, caught like a snapshot in an infinite frame. From this perspective, traveling at light speed isn't really traveling at all. It's more like being erased from the flow of reality, becoming something unchanging outside the narrative of the universe. Now, let's shift to how the rest of reality would look if somehow you were aware while frozen in time. To the outside universe, billions of years might pass, galaxies would spin and collide, stars would be born and die, civilizations might rise and vanish, all while, to you, no time has elapsed. You could launch on your journey and, from your perspective, instantly arrive at your destination, even if that destination were trillions of light years away. The trip would feel instantaneous, because time does not pass for you. Yet to anyone outside, you never truly reach light speed. You remain asymptotically approaching it, endlessly nearing, but never touching that line. This leads to a haunting duality. On the one hand, to you, there is no journey. You'd just be there. On the other, to the universe, you never arrive, because infinite energy is required to push you that far. This paradox shows why relativity forbids massive objects from experiencing light speed in the first place. It's not simply a speed limit like a highway sign. It's a wall in the very structure of reality, preventing objects with mass from slipping into a state where time disappears. Photons, which are massless, exist in this timeless domain naturally, but anything with substance is locked out.
Consider what this means in terms of causality, the relationship between cause and effect. If time halts for you, then causality collapses. You cannot perform an action because actions take time. A beginning, middle, and end no longer exist. This is why, even in theoretical discussions, physicists avoid saying a human could ever experience moving at light speed. The word experience implies the passage of time, and at light speed, experience itself would dissolve. Your existence, in that frame, would be reduced to a frozen imprint, incapable of thought, motion, or perception. Yet this thought experiment is deeply revealing. It highlights how differently reality looks depending on perspective. To us, bound by time, the idea of living without it feels impossible. But photons, the very messengers of light, exist entirely in this frozen frame. When a photon leaves a star billions of light years away and arrives at your eye, it does not experience that journey. From its perspective, the instant it is emitted is the instant it is absorbed. For us, that light traveled across vast cosmic distances and timescales. But for the photon, those distances collapsed to zero, and that time shrank to nothing. It is the ultimate reminder that reality is relative, and our human experience of flowing time is only one version of the truth. Now imagine standing on the threshold of this forbidden domain,
at 99.9999% of the speed of light. Already, you would see the universe warp into surreal shapes. Stars ahead of you would crowd into a single brilliant point due to relativistic beaming, while the rest of the cosmos behind you would fade into darkness. Distances would contract so severely that galaxies millions of light years away could seem within arm's reach. But the closer you edge toward light speed, the more you feel reality slip from your grasp. Energy required to push even a fraction faster skyrockets toward infinity, making the final step unreachable. And even if, somehow, you could leap across that last boundary, you'd cease to have any meaningful perception of the universe at all. There's a poetic tragedy to this. Light speed represents freedom, the ability to go anywhere, to outpace time itself, to skip across the stars in an instant. Yet the cost of that freedom is the destruction of everything that makes experience possible. To move at light speed is to trade away thought, memory, and consciousness for an eternal stasis. It is both the ultimate speed and the ultimate prison. This is why, though the dream of riding light beams has fascinated humanity for centuries, relativity shows us that the dream collapses into paradox. We are creatures of time, and the very fabric of physics ensures we remain tethered to it. And yet, this impossibility continues to drive imagination and science alike. Because if we cannot ride the beams of light, perhaps we can find another way, by bending space-time itself, by leaping through wormholes, or by discovering shortcuts hidden in the geometry of the universe. Einstein's equations, after all, don't just forbid light-speed travel for mass. They also suggest tantalizing loopholes where the rules might bend without breaking. But for now, the truth remains. For a human, reaching light speed would mean the end of time, and in that frozen void, existence itself would lose all meaning. If you follow the thread of Einstein's relativity all the way to its ultimate implication, you come to a conclusion that is as unsettling as it is profound. The very idea of a journey at the speed of light is an illusion for anything with mass. The reason isn't just about engineering limitations, like needing infinite energy or building materials strong enough to withstand the stresses. It's far deeper. It's baked into the structure of space-time itself. For a massive traveler, whether human, machine, or even the tiniest atom, the notion of actually experiencing what it's like to move at light speed collapses under the weight of physics. From the inside, if you could somehow make it happen, there would be no passage of time to mark the journey. It would be as though you never left, never traveled, never arrived, because the fabric of time for you would be completely gone.
This paradox is easier to grasp if we compare it to light itself. Photons, the carriers of electromagnetic radiation, always move at exactly light speed in a vacuum. They have no rest mass, which is the only reason they can occupy this extreme domain. But what's fascinating is that photons don't experience time at all. They don't age, they don't have a before and after. To a photon, the instant it is created by an atom and the instant it is absorbed by another atom are the same instant. There is no journey in between. From our perspective, that photon may have traveled for billions of years, crossing the void between galaxies before finally hitting a telescope. But from the photon's perspective, if such a perspective could exist, there was no travel, only emission and absorption. Now apply that to the thought experiment of you somehow becoming light-like. Your personal clock would stop ticking. Your heartbeat, your thoughts, your perception of duration, all of it would freeze. The trip, whether a kilometer or a billion light years, would collapse into the same kind of instant existence that photons experience. But unlike light, which has no consciousness to notice this timelessness, you would be erased as a subject of experience. There would be no awareness, no memory, no continuity. The journey wouldn't be something you lived through. It wouldn't be anything at all. And that's why physicists often describe the concept of traveling at the speed of light as meaningless for anything with mass. It's not just impractical, it's incoherent.
Our definitions of speed, distance, and time all depend on the ability to measure duration and separation. Take those away, and the language of motion itself ceases to apply. The equations of relativity show this rigorously. As you approach the speed of light, time dilation approaches infinity, length contraction approaches zero, and the required energy approaches infinity. Each of these factors alone is enough to prevent the crossing of the light barrier. Combined, they form an impenetrable wall. Imagine, then, what this means for science fiction fantasies of hopping on a starship, cranking it to light speed, and streaking across the galaxy. The fantasy always assumes that you could sit inside, maybe watch stars zip past, maybe feel the hum of the engines as the ship punches through space. But the actual physics paints a far stranger and bleaker picture. At light speed, there is no inside. There is no ship. There is no observer. There is no experience. To occupy that domain would be to cease existing as a being that perceives time. You wouldn't feel like you had arrived at your destination instantly. You wouldn't feel anything at all, because feeling requires time to pass, neurons to fire, and events to unfold. In the frozen frame of light, none of that can occur. From an outside perspective, things look just as strange, though in a different way. Observers watching you accelerate would never see you cross the line into light speed. They would see you asymptotically approach it, always getting closer, never arriving. To them, your ship would redshift, dim, and appear to slow down as you sank deeper into time dilation. From their frame, you would stretch out across eternity, never completing the push into light speed. So we have this symmetry of impossibility. From the outside, you never get there, and from the inside, there would be nothing left to experience if you somehow did. This leads to an almost philosophical conclusion. There is no there. Asking what it's like to move at light speed is like asking what it's like to divide by zero. The concept itself breaks the framework of meaning. We can describe the limits as we approach it. We can map the way the universe warps closer and closer to that unreachable horizon. But the horizon itself is forbidden territory. For photons, it is natural because they were born into it. For us, it is forever out of reach. And yet, there's something strangely poetic about this. It means that the very existence of time, of memory, of journeys and destinations, is tied to our slowness, to the fact that we move at less than light speed. If we could truly reach the ultimate velocity, we would lose the very fabric of what makes existence perceivable. To be human, to be massive, is to live inside time, to feel it flow, to experience a beginning, middle, and end. To be light is to have no story at all. In this sense, the barrier that keeps us from becoming light is also the barrier that allows us to exist as beings who can wonder about it.
That's the paradox. The idea of traveling at light speed collapses not because our technology isn't advanced enough, but because physics itself refuses to grant meaning to the question. And so the dream of making such a journey dissolves into a kind of nothingness. No motion, no time, no traveler. Just the stillness of timelessness, forever unreachable to us, yet essential to the way the universe itself is woven together. Even if you could somehow push past the barriers of relativity, the next problem waiting for you would be the sheer violence of space itself. At rest, interstellar space seems nearly empty. Just a few stray atoms of hydrogen, the occasional dust grain, or fragments from ancient stars. But at light speed, those tiny harmless particles become devastating projectiles. A single hydrogen atom striking you wouldn't feel like a speck of dust. It would carry the energy of high-energy radiation, slamming into your ship as if it were a cosmic bullet. Multiply this by the countless trillions of particles floating through the galaxy, and every fraction of a second would be like standing in the path of an infinite storm of invisible gunfire. The terrifying part is that even particles you can't normally detect would transform into lethal hazards. Cosmic dust, microscopic grains of silicate or carbon, would hit with the force of explosives. Something no larger than a grain of sand could unleash enough energy to vaporize entire sections of a spacecraft. This is because at light speed, kinetic energy skyrockets beyond comprehension. The familiar equation reminds us how much energy is contained in even a tiny bit of matter. Now imagine all of that unleashed in an instant, not because of a weapon, but because you were reckless enough to try outracing light itself. And it doesn't stop there. The radiation field surrounding you would intensify into a continuous barrage. Cosmic rays, gamma bursts, and stray photons would blue shift into the most extreme, high-energy states possible, bathing you in lethal radiation. The very fabric of space around you would feel like a wall of fire, not because you're plowing through thick matter, but because even the emptiness becomes deadly when your velocity approaches the ultimate speed limit. From your perspective, it wouldn't be just a collision, it would be annihilation, as matter and energy exchange in destructive bursts with every microscopic encounter. Some theorists point out that no material we know of could withstand even a tiny fraction of this. Our strongest alloys, our most advanced shielding concepts, all would crumble instantly under the unimaginable onslaught. Even the best ideas for interstellar travel today, like using magnetic fields to deflect radiation or plasma shields to redirect particles, would mean nothing at light speed. The incoming energy is simply too vast to deflect, absorb, or neutralize. The protective barrier would need to be infinitely strong, and that's as impossible as traveling at the speed of light itself. This transforms the dream of light-speed travel into something more like a nightmare. The universe becomes a minefield where every atom is a bomb waiting to go off. And even though space is almost entirely empty, the density of particles across billions of kilometers makes collisions inevitable. In practice, this means the faster you go, the more destructive the environment becomes, a paradoxical wall of death woven into the very structure of the cosmos. So even if you could cheat relativity, outsmart physics, and reach that elusive speed of light, you would find yourself in an unwinnable war with reality itself. Each grain of dust would be the end. Each atom, a weapon. The universe doesn't need to stop you. It has already set up a trap you can't survive. If you were somehow able to travel at the speed of light, one of the strangest and most unsettling consequences would be what happens to your vision. At normal speeds, your eyes receive light from all directions. The photons from objects in front of you stream toward your eyes, carrying information about the world ahead. But as your velocity increases toward the speed of light, the way those photons interact with you changes dramatically. Light coming from behind you or from the sides is distorted and shifted due to relativistic effects. But what happens directly in front of you is far more extreme. Light itself can't catch up. That means vision in front of you begins to fail in ways that don't even align with our everyday experiences. If you were somehow able to move exactly at light speed, the forward view would collapse completely into darkness or bizarre distortions, because photons that start ahead of you could never reach your eyes. To picture this, imagine trying to watch a movie where the projector is pointed straight at the screen, but you're moving toward the screen at the same speed as the light leaving the projector. The images would never actually reach you. You'd always stay ahead of them. In the same way, your forward vision at light speed becomes impossible, because no light could ever arrive from that direction. The photons are emitted, but from your perspective, they never get the chance to catch up and inform you about what lies ahead. Instead, everything in front would collapse into a void, leaving only strangeness around you. Now, what about the light from the sides or behind? That's where relativistic aberration takes over. As you approach the speed of light, all photons not directly in front of you begin to appear shifted into a narrower and narrower cone in your forward field of view. This is known as relativistic beaming. It means that as you go faster, light from every angle starts to focus into a distorted tunnel ahead of you, even though direct forward light is still absent. The result is that you wouldn't see stars in their natural places. Instead,
the night sky would warp into a brilliant but horrifying spotlight of compressed light. From your perspective, the universe seems to funnel into a single distorted direction, and yet, paradoxically, what lies directly ahead remains unreachable to your sight. As this effect grows more extreme, the light from stars behind you becomes blue-shifted, squeezed into higher frequencies. Radiation that was once harmless starlight could become ultraviolet, X-rays, or even deadly gamma rays as your speed approaches light itself. This means your visual experience wouldn't just be darkness ahead, but also dangerous, blinding brilliance all around, condensed into a cone of energy. Your eyes, if they could even function under such bombardment, would be overwhelmed by radiation. So rather than simply seeing nothing, you would face a mixture of blindness, distortion, and incomprehensible light, collapsing into strange geometric forms. But what's particularly haunting is the implication of the forward blindness. Humans navigate the world by sight, especially by looking where they're going. At light speed, that mechanism breaks down completely. Instead of being able to anticipate what lies ahead, you're trapped in a paradox, rushing forward infinitely fast, but receiving no new information about the very direction you're moving. To you, the future would be dark, because no photons from the path in front of you could ever bridge the gap. All you'd carry with you is distorted echoes of the universe behind and to the side, smeared together by relativistic compression. This strange blindness has another implication. Even if you could somehow ride a beam of light, you'd lose the very concept of forward motion as we understand it. Movement, to us, is always paired with the sensory confirmation of seeing what's ahead. But at light speed, that relationship dissolves. You're moving forward in space, yet your perception denies you the proof. In a way, you'd be traveling into absolute nothingness, cut off from the universe in the one direction you need most. The situation grows even stranger when you consider what happens to time. At light speed, time doesn't flow for you at all. That means not only would you not see ahead, but you also wouldn't experience the process of waiting to see ahead. There would be no delay, no frustration, no awareness of being blind. Just as photons don't age during their journey across billions of years of space, you wouldn't register the absence of sight, because you wouldn't register the passage of time itself. To the outside universe, it might look like you're racing forward at unimaginable speed, but to you, the flow of moments has ended. You would not even notice that vision had failed, because noticing requires time to move forward, and at light speed, time is gone. This paradox makes the forward blindness even more terrifying to think about. It's not just that you can't see what's ahead, it's that the very act of seeing no longer makes sense. Perception, after all, requires photons to arrive and be processed in a sequence of moments. But if photons can't arrive and moments can't flow, vision loses its meaning. In that sense, traveling at light speed erases not just the future, but the ability to perceive the future. From the perspective of outside observers, however, this whole breakdown plays out differently. To them, you never quite reach the speed of light. They would see you move closer and closer, your clocks ticking slower and slower, your energy requirements spiraling infinitely upward. From their vantage point, you'd simply approach light speed asymptotically, never fully reaching the threshold where this blindness becomes absolute. But if somehow you crossed that impossible barrier, the universe itself would stop making sense in terms of your perception. The laws of physics we rely on, the ones that govern vision, movement, and causality, collapse. And perhaps that is the final, inescapable truth. We can imagine what it might look like to race at light speed, but the reality is that the question itself is unanswerable within our physics. To see requires time, and to move at light speed means time cannot exist. To look ahead requires photons, and at light speed, photons cannot catch up. The result is a contradiction that underscores why light speed isn't just a physical barrier, but a perceptual one as well.
It's not only that our bodies could never survive the radiation, energy, or collisions with particles. It's that even if we could, our very experience of reality would dissolve into nothingness. Forward vision vanishing, perception breaking apart, and existence reduced to a timeless, lightless state. While forward vision would vanish into darkness at the speed of light, the universe behind you would undergo a spectacle just as surreal, though in a completely opposite manner. Photons that normally travel toward you from behind would now be caught in an intense relativistic compression. Instead of arriving evenly over time, as they would under normal circumstances, these photons would be swept into a dramatically narrowed field of view, funneled forward by your extreme velocity. The effect is known as relativistic aberration, and it warps the universe in ways that are both fascinating and terrifying. Imagine looking back while hurtling forward at near light speed. Stars that were once widely scattered across the night sky behind you would appear to squeeze together, as if the entire cosmos were collapsing into a dense, shimmering tunnel of light. Light from galaxies millions of light years apart would be compressed into a cone of radiance, all seemingly rushing toward your position. The familiar patterns of constellations, the comforting arrangements of stars you might recognize, would become unrecognizable, stretched and shifted beyond recognition. Every point of light would be brighter, more energetic, and increasingly blue-shifted as you approached light speed, transforming ordinary starlight into ultraviolet, X-ray, and eventually lethal gamma radiation. This compression of light isn't simply an aesthetic transformation, it's a profound physical effect. Each photon you encounter from behind now carries far more energy than it did at rest. As a result, not only do the stars and galaxies appear brighter, they also become increasingly dangerous. The accumulated energy from trillions upon trillions of photons would create a radiant bombardment unlike anything we experience on Earth. A ship attempting such travel, no matter how advanced, would require shielding that can withstand the combined effect of an infinite torrent of high-energy light, colliding particles, and gamma radiation compressed into a narrow forward cone. The very structure of matter as we know it might not survive such conditions. Even at a perceptual level, the universe behind you would appear drastically shifted. Because of the combination of time dilation and length contraction, light from objects behind you would arrive in rapid succession, effectively collapsing vast distances into a single moment. Galaxies that were millions of light years apart would appear almost adjacent, as if you were looking through a cosmic kaleidoscope that compresses entire swathes of the universe into a narrow slice. The shapes and positions of celestial bodies would distort, stretching into streaks or converging into points of blinding intensity. To the human eye, or even the instruments designed to mimic human vision, the scene would be simultaneously incomprehensible and overwhelming. As your speed increases closer to light, the relativistic Doppler effect amplifies the shift. Photons from behind you would be squeezed to shorter and shorter wavelengths, eventually becoming invisible to the naked eye and manifesting as extreme radiation. This means that what was once gentle starlight now becomes a dangerous torrent of energy. The very act of moving forward transforms the light of the past into an energetic wall that surrounds you. The universe behind, normally a serene backdrop of distant stars, becomes a compressed, violent, and dazzlingly bright spectacle, illustrating just how hostile light speed travel would be. Another fascinating consequence is the distortion of perspective. Objects directly behind you would no longer appear in their expected locations. The angles at which light reaches your eyes would be skewed due to aberration, making the stars appear to curve around you. The universe, in effect, would wrap itself into a visual cone, collapsing the three-dimensional spread of the cosmos into a warped, almost tunnel-like field. Distances would seem shorter in the direction of travel, yet the light you see would be packed with information from massive spans of space. Every point behind you becomes a compressed history of the universe, a record of light that left stars long before Earth existed.
This compression also highlights the temporal paradox of relativistic travel. While you experience extreme time dilation, with your own clock nearly frozen, the universe behind continues its expansion and motion. The light from distant galaxies represents events that, in your frame, are arriving almost instantaneously. It's as if you are witnessing billions of years of cosmic history in an instant, all funneled into a narrow strip behind you. The past of the universe becomes visible in ways impossible at normal speeds, but the effect is entirely inseparable from the dangers posed by energy accumulation and radiation. The interplay between this compressed light and the vanishing forward vision creates a surreal duality. Ahead, you see nothing. Behind, the entire universe is condensed into a dazzling, violent, and incomprehensible torrent of information and energy. Your experience of space is no longer intuitive. You cannot navigate by looking forward, because that light cannot reach you. Your knowledge of the universe comes solely from the distorted, compressed, and potentially lethal light streaming from behind. It's a sensory inversion. The past overtakes the future, the familiar becomes alien, and the cosmos itself becomes both your guide and your threat. This compression of the universe behind you also has implications for navigation. At light speed, conventional methods of orientation fail. Stars no longer occupy predictable positions. Distances are contracted. Light from behind is so concentrated that your ability to discern direction is overwhelmed. Any attempt to chart a course relies on signals that would be impossible to interpret in real time, because the very act of moving at light speed scrambles the visual and temporal information your instruments depend on. The universe becomes a blur of energy, a visual record of space compressed beyond recognition, and yet it is the only way your perception could exist at all. Even the physics of collisions compounds the challenge. Photons carrying this compressed light now arrive with incredible energy, and any stray particle caught in your path is magnified by the same relativistic factors. The universe behind you is not only a visual phenomenon, it is a stream of matter and energy intensified to extremes by your velocity. Every speck of interstellar dust, every cosmic ray, every photon contributes to a cumulative environment that would be lethal to unshielded travelers. The visual spectacle is inseparable from the physical danger. Ultimately, the universe behind at light speed becomes a paradoxical witness to your motion. It tells a story of the cosmos's history, compressed into an instantaneous display, but it is also a reminder of the impossibility of human travel at such extremes. The universe that normally stretches serenely across space is now concentrated, warped, and hostile. It illustrates the limits imposed by relativity. Even if one could approach light speed, perception itself is transformed. Energy scales explode, and the very act of moving forward in space is intertwined with both awe-inspiring beauty and existential hazard. Approaching the speed of light and actually reaching it are two fundamentally different realities, separated by a boundary that physics treats as absolute. When you get close to light speed, even at 99.999% of it, you are still operating in a domain where cause and effect, perception, and physical laws retain some familiar structure. At these speeds, all the strange effects of relativity become pronounced. Time dilation stretches seconds into years, length contraction compresses distances, and energy requirements soar. Yet, crucially, these effects remain measurable and finite. You can still, at least theoretically, exist, think, and perceive, though under extreme conditions. You are skimming the edge of impossibility, but the journey, in some sense, remains conceivable. As you accelerate ever closer to light speed, your experience of time slows drastically relative to the rest of the universe. From your perspective, a journey that takes years for observers elsewhere could feel like mere hours. Stars ahead of you appear to blur, distances shrink, and light from behind intensifies and compresses into a brilliant, potentially lethal stream. These are all profound effects, yet they do not destroy your existence outright. You can survive,
you can process information, and your consciousness continues to function, albeit under extreme relativistic distortions. Space, time, and energy become difficult to handle, but they do not vanish entirely. The universe remains intelligible, if only barely, and you maintain a causal link with the rest of reality. Crossing the threshold to actual light speed, however, flips all of this upside down. This is no longer a gradual amplification of effects. It is an absolute discontinuity in physics. Reaching the speed of light is impossible for any object with mass, because it would require infinite energy, a demand that breaks the laws of the universe as we know them. Unlike approaching light speed, where the effects stretch and intensify but remain finite, at the moment of reaching light speed, every concept we rely on to define experience and existence collapses. Time ceases completely, meaning you cannot perceive, think, or act. Length contracts to zero in the direction of travel, so distances vanish from your frame of reference. The universe ahead disappears into darkness because photons cannot reach you, while the universe behind is compressed into a blinding, dangerously energetic torrent. In other words, the difference is not just quantitative, but qualitative. Approaching light speed is extreme, but survivable. Reaching it is fundamentally incoherent. The distinction can be thought of in terms of continuity and limits. When you approach light speed, you are in a regime governed by hyper-relativistic physics. Time moves slowly, but exists. Energy requirements are extreme, but calculable. Collisions with particles are devastating, but finite. You are testing the edges of physical laws, pushing them to the brink. But to reach light speed is to step outside those laws entirely. The formulas that govern mass, energy, and momentum break down. Acceleration no longer makes sense, time no longer exists, and causality is effectively destroyed for you. The journey transforms from an extreme experience of physics to a paradoxical impossibility. There is no continuum connecting the state of being just below light speed to the state of being at light speed. The latter is a forbidden region of the space-time landscape. This boundary also underlines why even our imagination struggles to grasp true light-speed travel. When approaching it, we can extrapolate. Stars streak, distances compress, time slows, radiation becomes intense. But all of these can be described and understood through the equations of special relativity. There is a limit to how far we can go, but we can still talk about the effects. Reaching light speed, however, is a conceptual dead end. The mathematics that predict time dilation and length contraction yield infinities. The universe becomes singular in a very literal sense. Energy goes to infinity, distance contracts to zero, and time stops. These are not extreme forms of familiar phenomena. They are failures of the phenomena themselves. Consider also the human perspective. At near light speeds, an observer can still retain some agency. They can steer, make decisions, communicate, and perceive. At true light speed, none of this is possible. Consciousness itself depends on the sequential passage of time, neurons firing, thoughts forming, reactions unfolding. With time frozen, consciousness cannot function. To experience light speed is therefore impossible. It is not merely a physical barrier, it is an existential barrier. You cannot occupy that state as a sentient being, because all processes that define sentient existence require time to progress. From an external observer's point of view, this distinction is equally stark. As you near light speed, they see you asymptotically approaching the limit, moving ever more slowly in their time frame. Your mass increases, your acceleration slows, and you require increasingly vast amounts of energy to continue your push. But you remain within a comprehensible framework. Observers can calculate your trajectory, predict outcomes, and even imagine what you would see if they could enter your frame. At the speed of light, however, observers would still see you never quite reaching it. You remain forever on the asymptote, trapped at the edge of possibility. The universe protects itself from violation of its own rules, preserving the integrity of physics by ensuring that nothing with mass ever actually occupies the forbidden lightspeed domain. In practical terms, this distinction has implications for both science and science fiction. Stories about warp drives, photon rockets, or light-speed starships often blur the line between approaching light speed and attaining it. Writers may describe instantaneous travel or frozen time as if it could be experienced, but relativity shows that the former is possible in principle, while the latter is forbidden entirely. A ship can approach light speed and experience the extreme consequences: time dilation, energy requirements, cosmic radiation, and relativistic visual distortions. But it cannot cross the line and reach the speed of light itself. That line is not simply a technical hurdle, it is a law of the universe, embedded in the very structure of space-time. Thus, the difference between near light speed travel and actual light speed travel is profound. Near light speed travel amplifies the strangeness of the universe to extremes, but it leaves the traveler intact, conscious, and technically capable of interacting with the universe. Actual light speed travel annihilates experience and meaning, transforming existence into a state where time, perception, and even movement lose all definition. Approaching light speed is a challenge. Reaching it is a contradiction. The effects are not merely more intense, they are qualitatively different. The difference between an extreme adventure and the ultimate impossibility. This distinction also frames our understanding of the limits of exploration. Humanity may one day develop technology to approach light speed, enabling interstellar travel in a form that pushes the boundaries of physics. We could stretch our lifespans relative to the universe, compress cosmic distances, and witness the universe in ways inconceivable at slower speeds. But true light speed travel is forever barred, a domain reserved for massless particles like photons, whose existence is unbound by the sequential passage of time. The universe sets a firm limit, defining a boundary between what can be approached and what can never be occupied. It is a boundary written into the fabric of reality itself, separating possibility from paradox. While true light speed travel remains fundamentally impossible for anything with mass, theoretical physics does offer some imaginative workarounds that sidestep the problem by bending space itself rather than trying to break the cosmic speed limit. One of the most famous concepts is the Alcubierre warp drive, proposed in 1994. Instead of accelerating a spaceship to light speed, a warp drive would compress space in front of the ship and expand it behind. In this scenario, the ship itself remains stationary within a warp bubble, while the surrounding space moves. From the ship's perspective, it isn't moving faster than light locally, so it avoids the infinite energy and time-freezing paradoxes of actual light speed travel. In effect, the universe itself does the moving, allowing the ship to traverse vast distances in short durations without ever breaking relativity. Wormholes are another speculative concept. A wormhole is a tunnel through the fabric of space-time, connecting two distant points in the universe. If such structures exist and could be stabilized, a huge if, as they likely require exotic matter with negative energy density, they would allow instant travel between points separated by light years. Again, this doesn't violate the speed of light locally. It merely creates a shortcut through the geometry of space-time itself. Instead of racing across the universe, you step through a corridor where the distance has been drastically reduced. From the traveler's perspective, the journey could be instantaneous, while the surrounding universe experiences the passage of normal time. Both of these approaches highlight an essential point. The limitations imposed by light speed are absolute when it comes to local motion, but physics does allow for creative manipulations of space itself. Instead of accelerating a mass to impossible velocities, these theoretical methods bend the rules in ways that preserve causality and relativity. The challenge lies in the energy and technology required. Warp drives would demand enormous amounts of energy, potentially equivalent to the mass energy of planets, and stable wormholes might require forms of matter that we have yet to discover. While purely speculative for now, these ideas illuminate a fundamental principle. The universe sets constraints not to punish exploration, but to define the rules of how it can be navigated. By understanding the true nature of light speed limits, physicists can explore alternative pathways that respect the laws of relativity while still pushing the boundaries of distance and travel. They are tantalizing glimpses of what might be possible in a universe where bending space, rather than breaking physics, becomes the ultimate key to interstellar journeys. Even after exploring every conceivable consequence of traveling at light speed, the infinite energy required, the mass increase, time dilation, length contraction, forward blindness, radiation bombardment, and the relativistic compression of the universe behind you, one truth remains inescapable. Light speed is fundamentally unattainable for anything with mass. The laws of physics erect a boundary that cannot be circumvented, and the universe enforces it with ruthless precision. From every perspective, whether inside the hypothetical craft, outside observing it, or imagining the experience as if you were a photon, the conclusion is the same. There is a limit to how fast we can go, a limit to how we can perceive motion, and a limit to the experience of time itself. Yet, paradoxically, this very boundary is what defines our capacity to explore and understand the cosmos. The speed of light is not merely a speed limit, it is a cosmic measure of causality and temporal order. Without it, the universe would lose its coherence. Without the rules that prohibit mass from reaching light speed, time could unravel, space could warp uncontrollably, and the sequence of cause and effect, which underpins all science, would collapse. By imposing this ultimate limit, the universe sets the stage for exploration, reasoning, and discovery within a framework that is consistent and intelligible. It tells us that exploration is inherently bound by the structure of reality itself. The impossibility of traveling at light speed also reframes how we think about interstellar ambitions. It means that humanity's reach into the cosmos will always be constrained by relativistic principles. Even if we develop the most advanced propulsion technologies conceivable, antimatter drives, fusion-powered starships, or hypothetical warp bubbles, we will never cross the barrier of light. Every journey will be an approximation, a close approach to the unattainable frontier, with effects growing more extreme the closer we get. Time will stretch, distances will compress, and the universe will reveal itself in distorted and extreme ways, yet the ultimate limit remains fixed. This raises a profound philosophical question. What does it mean to explore when the ultimate velocity is unreachable? If light speed is forbidden, then the galaxy cannot be raced across in a single lifetime, and civilizations cannot simply skip across cosmic distances instantaneously. Exploration becomes a slower, more deliberate endeavor, reliant on ingenuity, patience, and the creative manipulation of space rather than brute acceleration. Concepts like warp drives and wormholes, though speculative, underscore this. The key to reaching distant stars may not be to move faster than light, but to bend the fabric of space-time, to find ways of navigating the universe within the boundaries that physics imposes. And yet, this limit is not discouraging. It is profoundly inspiring. It forces us to think beyond conventional motion, to innovate in ways that respect the universe's rules while still expanding our reach. It reminds us that human curiosity and ingenuity are not measured merely by speed, but by creativity, understanding, and the ability to adapt. The unattainability of light speed highlights the vastness of the cosmos, the scale of interstellar distances, and the sophistication required to traverse them. It reminds us that exploration is an ongoing endeavor, a challenge that requires both intellect and imagination. Ultimately, the cosmic speed limit serves as a mirror for human aspiration. It confronts us with the reality of our constraints,
yet simultaneously illuminates the extraordinary potential within those constraints. It asks us to reimagine what it means to journey, to discover, and to reach beyond ourselves. We may never travel at light speed, and yet our exploration of the universe can continue in ways that are profound, meaningful, and endlessly compelling. The ultimate mystery, then, is not merely the impossibility of racing through space at the velocity of light, but the question it leaves us with. If we cannot break the ultimate speed limit, what does that tell us about the true limits of human exploration? Are we defined by the boundaries we cannot cross, or by the creativity, determination, and ingenuity we bring to navigating within them? The answer is not found in breaking the laws of physics, but in understanding them, respecting them, and using them to chart a path forward through the infinite expanse of the cosmos.
In this light, the speed of light is more than a barrier. It is a challenge, a guide, and a profound statement about the nature of reality and the possibilities of human endeavor. It reminds us that exploration is not just about moving fast. It is about thinking, observing, and innovating in harmony with the universe itself. Every attempt to approach this ultimate speed, every thought experiment, every theoretical construct, only deepens our appreciation for the vast, intricate, and beautiful rules that govern existence. The frontier is not just out there among the stars. It is also in the questions we ask, the ideas we pursue, and the understanding we achieve as we navigate a universe bound by the ultimate speed limit, yet filled with infinite potential for discovery. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.